Yeah, okay. Recording begins. Okay, so welcome once again. All right, on this lovely morning. Okay, to the second part of fluid dynamics, MA4002. Now I've been hearing people going around saying, "Oh, fluid die. All right, she'll die." Okay, no such thing, yeah, no such thing. Okay, I don't think there's any recorded history of students, right? Okay, really suffering until like that, all right, when they took fluid dynamics. Okay, all right, stop calling fluid die. Okay, just giving that module a bad reputation. Call it fluid dynamics. Okay, even though I must admit, right, anything, I'm not too sure whether you guys realize, for engineering modules, right, anything that ends the title of the module, if it ends with something like mix, all right, got to be a bit careful, right? Thermodynamics, fluid mechanics, aerodynamics. What else? Something mechanics. Okay. All right. Because anything that ends with mix, right, tends to belong to classical engineering mechanics. Okay, so they tend to be very classical and slightly more traditional and very extra. But let's do our best. Okay. Okay, so this will be the scope of our lecture today. I wouldn't call it today because actually we have got what 6-7 lecture sessions. All right, we have got 4 chapters. I don't think I want to rush. I think you guys understand it. The lecture materials is a lot more. It's a lot more important than for me to just wrap things up. Okay, so I'm going to take my time. Make sure you guys understand as much as possible. So this will be the scope for this chapter. I think that's what I should be saying. Okay, we're going to look at some of the governing equations when it comes down to fluid dynamics. Okay, we're going to be looking at some ways, okay, that we can make use to describe, all right, general fluid motions. I think that's very important. Okay, now in terms of governing equations, we do have quite a few, but there are 3 very important ones, right? Conservation of mass, conservation of momentum, right, and conservation of energy. I'm going to focus on conservation of mass and momentum because, right, from the governing equations that we get out by considering these 2 conservations, we are going to get very useful equations that we can solve engineering problems. Okay. Now, one of the most important governing equations that we typically deal with when it comes to fluid mechanics or fluid dynamics, and in fact, aerodynamics, all right, it's actually the Navier-Stokes equation. So I'm going to talk about the derivations of Navier-Stokes equation and how we can simplify them and use it to solve engineering problems, right, in an analytical manner. Okay, hang on for a while. I think the people who just joined the lecture, let me just double check that they're using NTU signings. Huh? Yeah, I've got to be careful because sometimes strange people just drop by. Do you know that? I'm quite sure you guys know, right? Like, they're like students from other universities that attend my lecture just because some students share the link with them, and vice versa. I'm not too sure whether you guys ever attended, like, do you guys have like friends in NUS, SUTD, SIT, and then say that, hey, I want to like check out your lecture, man. Can you just send me the link? I'll secretly just go in. Has anyone done that? No, you'll not be incriminated. Okay, I'll just out of curiosity. Okay, all right. I'm just curious because we've been like seeing strange names, strange people popping in. Okay. Anyway, going back to the lecture. Oh, hang on. Going back to lecture now. Going beyond Navier-Stokes equation, which is the all-encompassing equations that describes pretty much all general fluid mechanics. All right, we're going to touch upon simpler versions of Navier-Stokes equations known as Euler equation, okay, Bernoulli's equation. All right, and I'm going to round off this chapter by speaking a little bit more on what typically happens when we try to simplify Navier-Stokes equation. And as engineers, we should be cognizant of the fact that even those while simplifications makes everything simple, and we are able to get analytical equations that allow us to arrive at the solutions quite easily and things like that. Okay, there are rather significant issues when it comes down to simplifying the Navier-Stokes equations way too much. All right, because if you keep simplifying it, okay, thinking that things are going to be easier and easier. All right, always bear in mind that these simplifications are going to give you solutions They're getting more and more unrealistic. All right, so a compromise needs to be struck, yeah? Okay, when it comes down to simplifications, okay? Okay, governing equations, as I've mentioned, right? When it comes down to fluid dynamics, okay, three very, very important conservation laws: conservation of mass, conservation of momentum, and conservation of energy. Okay, mass can't just pop in and disappear from nowhere. Okay, just like momentum. Okay, the same goes for energy. All right, energy. I think this is something that we learned since secondary school, isn't it? Okay, energy just you can't have free energy that pops into this universe, isn't it? Okay, and you can't have energy that just simply disappears somewhere. All right. Okay, I'm not going to go into like quantum mechanics, right, whereby to say that there's always energy fluctuations in the background, things like that. Okay, I'm not an expert in that. Okay, I'm talking about macroscopic energy, energy that that we're used to seeing. Let's say propane gas, we burn it, and things like that. Those type of energy. Yeah? Okay, and within this module, please bear in mind that we need to draw a distinction between various types of flows. For example, right, we need to know that there's actually a difference between a steady flow and an unsteady flow. Okay, and unsteady flow is one whereby, let's say, flow variables such as velocities, pressure, what else? Something else, vorticity, let's say. All right. So steady flows have got these flow variables that vary with respect to time. Okay, steady flows, of course, is the other way around. Okay, they remains invariant with respect to time. Okay, we also have to distinguish between incompressible and compressible flows. So I believe in Prof. Tuan's lecture, he covered compressible flows. Okay, for this particular part, all right, we'll be dealing with incompressible flows. Okay, so when it comes down to compressible flows, all right, clearly density varies. For incompressible flow, all right, it's the other way around. Density remains fixed. And now, even though, all right, there's no such thing as 1 or 2D flows, okay, all right, in the real world, okay, all flows are three-dimensional. There are circumstances whereby we are able to assume that bulk of the flow is 1D or 2D, and hence we can use this assumption to simplify some of the equations, okay, all right. But we need to know at the back of our mind that all flows are inherently 3D, okay? It's just how 3D are we talking about, okay? Later on, we're going to touch upon potential flow, whereby we will distinguish between rotational fluids or irrotational fluids. Now, rotational fluid, rotational flows and irrotational flows, okay, does not simply mean that whether they are spinning or not, okay, all right, rotating or not. No, we're actually looking at whether the fluids, all right, control area or control volume are undergoing angular deformation. So there's some subtle but important differences, okay, that we have to be careful of. Okay, so again, conservation of mass and momentum are probably the most important concepts within this particular module. Okay, I'm not going to go into energy, right, when it comes down to fluid dynamics, because this is probably closer related to combustion, okay, which we're not going to deal here. Okay, so in fact, if we look at the equations from conservation of mass and momentum, and all right, under the right circumstances, combine them together, we're going to get this all-encompassing Navier-Stokes equations. All right, supposedly Navier-Stokes equations, all right, are able to describe almost all fluid flows out there. Okay, it has never been verified to be correct. Okay, all right, people just clobber these terms out over the years, but clearly, many studies have said that this describes fluid flow, or just done too well. All right, that's why people just kept using it. Okay. Now let's take a closer look at how we describe fluid motion. Okay, so with respect to the figure on the top there, right, imagine the black line is the trajectory, is the path or along which the particle, the blue particle, travels. And the red arrow there is the instantaneous velocity vector. So imagine, right, this blue particle, happily traveling along this black line, going about its day, and then we say that, look, all right, stop, freeze it, pause, all right, Zoto, all right, okay, and then we analyze its motion, okay, all right. So what's going to happen is, okay, we can see that the velocity of this particle, all right, at any point in the 3D space, and of course time. Right? We'll talk about time later, but let's look at the position. Right, the velocity at any point in the 3D space within which this particle is actually traveling along, okay, can be described by using u, v, and w velocity components in the x, y, and z directions, respectively. Okay, now you guys know your vectors, I'm quite sure. All right, if that's the case, that means we can express the velocity vector, this red arrow over here, we can describe the velocity vectors of this blue particle, all right, using in this vector format, whereby v bar, I'm just going to call it v bar, okay? Otherwise it's going to be quite a mouthful, all right? I don't want to call it cap v bar arrow. That's just too much, okay? That's just too much, okay? All right, I'll just call it v bar, okay? V bar. So this is the 3D velocity vector expressed in general terms. So v bar, okay, can be written as ui bar, where I bar, j bar, k bar are the unit vectors in the x, y, and z direction. So we have ui plus vj plus wk. So u, v, w are the velocity components in the three directions, and I, j, and k are the unit vectors in these three directions. Okay, I think this should be straightforward for you because this is something that we have done earlier, isn't it? Okay, maybe even in your year one engineering mathematics. Yeah. Okay. Now, if you think about it, the u, v, and w component, okay, in these three primary directions, certainly, okay, all right, they can be a function of their locations, all right, in terms of x, y, and z, as well as time, okay, because it can be associated. This particle can be traveling in an unsteady flow. So the velocity fluctuations, all right, can be a function of time. So if you want to express this, all right, okay, in even more general terms, okay, we can write v bar as u as a function of x, y, z, and t, all right, unit vector I plus v as a function of x, y, z, and t, unit vector j plus w, okay, as a function of x, y, z, and t, unit vector k. Okay, so this is the absolute general term, isn't it? Right, it encompasses all sorts of flows, right? Compressible, incompressible, steady flow, unsteady flows, 3D, right, and so on and so forth. Okay. Now, since we're dealing in vectors, right, that is I, j, and k, right? Okay, how do we find out the unit? How do we find the magnitude? Okay, of a vector. In this case, we're talking, all right, to be more specific, the velocity vector v bar. Okay. Now, if you guys try to recall back your vector knowledge, right, that you guys have done over the years, okay, I'm quite sure you guys will realize that to find out the magnitude, all right, of any vector, all right, in this case, the velocity vector, okay, it's just a matter of taking the root mean square, okay, all right, of these various terms. So in this case, the magnitude of v bar, which is the velocity vector v, let's just write it as just v without the bar, or you can write it as v bar with the two vertical lines on the left-hand side, on the right-hand side. All right, we can define this as square root of u squared plus v squared plus w squared. Okay, so far so good? Yeah? Or you guys have fell asleep? Oh no. Okay, I assume that you guys are watching this. Okay. Okay, let's move on. Okay. I think this is still manageable. Okay, bear with me. I know that's too many. I've exceeded the quota for dealing with partial derivatives for the day, but just bear with me, okay? Now, since we already defined our velocity vector, all right, we came up with the vector expression. All right, if you think about it, what's the next best thing that we can do? If we have got the velocity vector term expression, we should differentiate it because when it comes down to fluid dynamics, okay, all right, the fluid motion, the particle, all right, is likely to undergo acceleration if you think about it, okay. And how do we find acceleration? Okay, in fluid dynamics terms, okay, acceleration a bar, okay, is nothing but the total derivatives of the velocity vector. So you can see we don't use small d, we use big D, because acceleration of fluids, all right, is actually quite different of acceleration, all right, associated with solid objects. Because remember, fluids can be deformed. Okay, so velocity gradients come into play. Right? Unlike a solid body, if it goes this way, accelerating this way or that way, it's fixed. The whole solid moves together. But for fluids, all right, the control volume may undergo deformation, all right, as it accelerates in a certain direction. So you've got to be careful. That's why the acceleration expression looks a bit more complicated. Okay, so to define it formally, acceleration vector of a fluid particle, let's just call it small a bar, is nothing but cap d v bar by cap d dt. Oh, hang on, am I saying right? Let me say again. Acceleration vector a bar is nothing but cap d v bar by cap d t. Oh, I got that right. Okay. And this term, okay, this total derivative is nothing but, we can expand it and it can be expressed as del v bar by del t. So this will be the unsteady velocity term plus del v bar by del x, all right, times del x by del t. Okay, all right. So this will be the what? This will be the term that is related to the in the x direction. All right, but we have two other directions, isn't it? Okay, so we have two more terms, which is plus del v bar by del y times del y by del t plus del v bar by del z times del z by del t. Okay, so this is the definition of total derivative or total acceleration. Okay, now we know that from here, I'm quite sure you can see that, hang on, we have del x by del t term here, del y by del t, and of course del z by del t. These are nothing but just the velocity vectors u, v, and w, the three directions. So that means we can replace them by the velocity components, and the total acceleration can be simplified to this. So this gets simplified to this. Okay, now we see the u, v, and w terms here. Okay, but hang on. This cap v bar term here is actually the velocity in all three directions. Okay, and if you think about it, if we have velocity components in the x, y, and z direction, okay, we should have acceleration in the x, y, and z directions as well. So this is just a general vector expression, all right, that describes acceleration in all three directions. If you want to be specific, okay, we can extract from here the accelerations in the x direction, acceleration in the y direction, are clearly the accelerations in the z direction. Okay, and we can come up with this respective acceleration components. So ax is nothing but cap d u by cap dt, and this is nothing but del u by del t. As you can see, there's only v velocity component, u velocity component here, plus u by u into del u by del x, plus v into del u by del y, plus w del u by del z, and so on and so forth. Okay, as you can see, all over here, we only have the u terms in the x associated in the x direction. As for the acceleration in the y direction, we only have the v terms here. Okay, and as for z direction, clearly we're going to have w terms here only. Yeah. Okay. Okay. Now. From the previous slide, we've already seen, right? Acceleration is nothing but the total, all right, derivative or total differentiation of the 3D velocity component v bar. Okay. Now, if you the total derivatives of any variable, all right, basically can be described as this. All right. So whatever that's within the bracket, it can be velocity vector, it can be pressure, it can be whatever. Okay. Okay. Vorticity, anything that has, well, yeah, it can be of other things. I don't want to confuse you, okay? But there are other terms as well, okay? But let's say there's vorticity, there's velocity, there's vorticity, and so on and so forth, okay? Now, some of you guys may have borrowed textbooks, or you guys have read up textbooks, okay? Different textbooks, different people, all right, use different terms. Over here, I use total derivatives, okay? Some textbooks may use terms like material derivatives, substantial derivatives. They are all the same. Okay, they're all the same. Okay. After thinking about it for a while, I decided to use total derivatives because it seems more intuitive to use the word total derivatives because, as you can see, the total derivatives, all right, comprises of many different derivatives. So and then we add them up together, right? So total derivative seems logical, all right, at least in my books, okay? So yeah, so that's why I want to, so we just use total derivatives now. So now all these are partial differential terms. And sometimes when you try to write out all these partial differential terms, things gets, I don't know about you, my hand gets tired when I try to write that down. And also it's quite an eyeful, isn't it? Okay, we can actually re-express, all right, total derivatives, all right, in vector form in this way. So as you can see, the total derivative term here will be this. So it remains the same on the left-hand side of the expression. We've got the unsteady term here, all right, because it's a function of, it's a partial differentiation with respect to time t. It stays the same. It's the last three terms that we simplify in vector form. So these three terms can be described by this instead, whereby we have v bar dot gradient operator, right? Or we just call it grad, okay? G-R-A-D, grad, yeah. Okay, and this could be velocity and so on and so forth, okay? All right, by definition, the gradient operator, the grad term here, the grad function here is nothing but, okay, right, del by del x of the variable I plus del by del y of the variable j plus del by del z of the variable k. All right, so this earlier function, all right, okay, the partial differential base expression for total derivatives can be re-expressed in vector form as this. Which actually, if you think about it, looks far more elegant than the one that's based on partial differential terms because, well, for one, it's shorter. Okay, for one, it's a lot shorter, easier to write, easier to remember, and things like that. And I think it looks a bit more elegant. Yeah. Okay. So now I'm quite sure it becomes very, very clear now. Okay, that this term really sticks up because it's the only partial differential term on the right-hand side of the expression. And this term is nothing but the flow or the unsteady flow component if you're dealing with unsteady flow. If you are using, if you are dealing with a steady flow, all right, this term will go to zero, of course, okay? Now, this is just mathematics, right? This is just mathematics. So what if you get the expression if we do not know what the terms really mean? All right, I hope you guys agree with me on that. So I think it'll be timely to basically explain the terms. All right, what do you mean by total acceleration? Well, how many, what are these two terms on the right-hand side? Okay, now, so in fluid mechanics, okay, total derivatives or total acceleration is nothing but the summation of what we call the local acceleration defined by the unsteady term, all right, and the convective acceleration term, which is defined by the second term. Okay, now what do you mean by local acceleration? What do you mean by convective acceleration? It seems strange, isn't it? Because we're so used to seeing solid bodies undergo a very, very straightforward acceleration, isn't it? 2 meters square, 2 meters per second square, that's it. All right, what could be simpler than that? No, there's only one component. No, when it comes out to fluid dynamics, things are a little bit different, okay? Accelerations has got these two components. What is local acceleration? Now, a local acceleration, okay, means that that acceleration term, okay, is dependent upon time, okay? What kind of scenario will this local acceleration be important, okay? Let me see if this works. Imagine there's a pipe, okay, where, you have an orifice plate. Let's say you have a valve. And the valve, let's say, is, not to say that it's totally shut, but let's say it's closed. All right, not say it's closed. It's choked. All right, it's choking the flow such that, all right, initially there's only this amount of water going through. And if you think about it, if there's only this amount of water going through, all right, surely the velocity, all right, after this valve, all right, will not be too high, isn't it? But what happened is, okay, once I open up the valve fully, all right, as what you guys have seen early on, okay, what happened is, okay, the acceleration, all right, there will be an acceleration in the flow velocity, okay, at the same location, all right, Okay, simply due to because, right, there's a larger flow rate. Not because we're looking at another location elsewhere in the flow, but because simply, all right, something happens. Okay, all right, and the velocity increases or decreases depending on whether you're opening a valve or closing a valve. Okay, or any other scenario. So in this case, all right, the change in velocity or acceleration is only dependent upon time, and we call this local acceleration. Now, how about convective acceleration? Now, the word convective should provide you guys a clue, isn't it? All right, that means this acceleration surely has got something to do with the motion of the fluid particle, and you will not be wrong if you think that way. Okay, so what happened is, okay, convective acceleration is an acceleration component due to the displacement of the fluid particle. Okay, why is that? Now imagine we have a fluid particle, right, that's traveling in a convergent cone, let's say. All right. When the fluid particle is located here, all right, it has a certain velocity. But as it moves, all right, increasingly forward into the convergent section, what's going to happen is, all right, the velocity will increase. Why? Because the cross-sectional area, all right, basically decreases. And if we know mass continuity, we know that mass must be constant. If the cross-sectional area decreases, all right, the flow velocity must increase. Okay, and if you think about it, this acceleration component is not dependent upon time. It's dependent upon the location of the fluid particle. And hence, this particular acceleration component will be known as the convective acceleration component. Okay. Oh, I forgot to click on the button. All right. So as you can see, the velocity increases over here. Okay. All right. So now we can take a look at some example just to illustrate the various expressions that we have gone, I wouldn't call it derived per se, but we have defined so far. Okay, just a very simple example. And after this example, we can go for a break. Yeah, okay. Now let's consider a two-dimensional, all right? Sometimes I just write it as 2D. They are all the same thing. So it's let's consider a two-dimensional flow. And this flow is steady. And the best thing is this flow, all right, has a velocity vector v bar that's described by this expression over here. V naught into x over L, r unit vector, minus y over L, j unit vector. Right, because it's 2D flow, right? So clearly there's no k vector. Okay. And we're told that V naught and L are constant. So these are constant, these are constant. Fantastic. We all love constants, right? Okay. Now, based on the given velocity vector term, we're asked to find a few things. A, we're asked to determine the locations at which the speed is equal to V naught. That's the first thing. Second thing, we're asked to determine the acceleration field, all right, as well as the magnitude and direction of the flow. That's quite a chunk flow, isn't it? Don't worry, all right, we just solve it systematically. Don't just look at it and say, that, wow, so many things to find. All right, I'm going to run away. No, okay, don't run away. No, don't run away, okay? Live up to the challenge, rise up to the challenge, and overcome the challenge. Geez, it sounds like some army unit motto. I apologize for that. Okay. Last but not least, okay, I will ask to sketch the flow field. Sketch, not plot, huh? Okay, so don't whip out a graph paper, you know, and take a, I don't know, take a flexi curve and start drawing stuff. No. Sketch, all right, not plot. Okay. Sketch the flow field in the region defined by this, right? In this quadrant, if you think about it, x greater or equals to 0, y greater or equals to 0. So if you think about it, it must be in the positive x and y region, that particular quadrant. Okay, but first thing first, okay, let's find out the locations at which the speed is equals to v naught. Okay, so now speed. What is speed? Is speed a vector term or magnitude term? It's a magnitude term. Okay, so speed, all right, is nothing but defined by this equation, as we've seen earlier on. Okay, but of course, this is being defined for a 3D flow. We're talking about 2D flow over here. So as I've mentioned earlier on, there's no W term. So the magnitude of any velocity vector can be simplified to this. V is nothing but square root of u squared plus v squared. And we do know the magnitude of u and the magnitude of v. don't we? Okay, so we just take u and v, plug into here, square them. Then after that, simplify them because there's this square root, or you can get v naught divided by L of the square root. And you're going to get v naught divided by L into the square root of x squared plus y squared. Okay, so this is the magnitude of the velocity vector, which if you think about it is speed. Okay, now this is the general expression for speed because it's dependent upon x and y location. Okay, now for part A, okay, we're asked to find the locations, that means the value of x and y. Okay, at which speed is equals to v naught. So that means we have to take, let's check this magnitude and equate it to v naught, right, as this. I'm quite sure you know that we can simplify some of the terms. I can see some common terms here, especially v naught. Okay? And if you do that, simplify the stuff, shuffle the terms around, you're going to get x squared plus y squared equals to L squared. Hang on for a minute. If you have studied your O levels and A levels, okay, surely. I have no idea what kind of math is that. During my time, it was called F math, something like that. Okay? I'm not too sure what it's called for you guys. Nowadays, it's just so confusing. H something or whatever. I have no idea. Okay, but I think you guys should know what I mean. I'm quite sure that you guys must have learned early on that x squared plus y squared equals to a constant, whereby that constant can be described as, in this case, L squared. It describes a particular distribution of points. In fact, x squared plus y squared equals to x squared plus y squared equals to L squared. It's nothing but what? Right? It's nothing but a circular loci, all right, of points, okay, that centers about the origin, okay, and this circle, all right, will have a distance, all right, a radial distance of L from the origin, okay, to any point along this circle. So basically the radius is L, okay, so that means any point along this dashed line would have satisfied this and would have a speed of v naught. Okay, that's how we interpret, all right, the solution for part A. Okay, now if you want to find the velocity directions at any point along these points, okay, you can basically use this formula. I'm quite sure you guys know this, right? Okay, if you want to find the directions, nothing but the inverse tangent of the velocity components. In this case, we have a negative sign here. That's because the v velocity magnitude here has got a minus sign. Okay. Okay, so that's for part A. Now, how about part B? We're asked to find the acceleration field and so on and so forth. Now, if you guys recall from the earlier slide, this will be the acceleration field expression. Okay, but since we're talking about 2D steady flows, if you think about it, that means del V bar by del T equals to 0. Okay, so it's a steady term, so the unsteady term goes to 0. It's a 2D flow, that means any velocity component in the third direction, that means with respect to Z, okay, must be equals to 0 as well. So we can simplify this expression into this, whereby A bar is nothing but U into del V bar by del X plus V into del V bar by del Y. Okay, we know what's our U, we know what's our V. Okay, we know what's the velocity vector V here, plug it in, simplify, we're going to get this acceleration vector. V naught square X divided by L square, unit vector I plus V naught square Y divided by L square, unit vector J. To find the magnitude, it's very, very simple. It's basically the same as defining the magnitude of the velocity vector, isn't it? Okay, basically it's just the root mean square of these two components again. Okay, so we do the root mean square, simplify, we're going to get this. That means the magnitude of the acceleration is nothing but V naught squared divided by L. Okay, all right. How about the direction of the acceleration vector? Just like this. Okay, it's the same way, right? Of course, in this case, we're not using U and V. We're using acceleration in the Y direction and acceleration in the X direction. Okay, and eventually it worked out to be the same as the inverse tangent of Y over X. In this case, there's no negative sign here because look at the acceleration components, right? The two components are all positive, right? So there's no need to put in a negative sign here. Okay, all right, just to illustrate, since we're going to ask, since we're asked to sketch out some of these accelerations, sketch the flow field, sorry, okay, for a certain region. So maybe all right, things will become clearer if we worked out some sample points. Okay, so we pick out some sample points from the quadrant, this quadrant. Okay, and we try to find out what's the value of v, what's the direction of the velocity vector. We try to work out the magnitude of the accelerations and the direction of accelerations. So just plug in some sample points, and eventually, all right, you're going to get something like this. Okay, so all right, this will be for the velocity terms, the velocity vectors, all right, and they're represented by these solid black arrows. As for the acceleration vectors and the directions, all right, there'll be these dash vectors. Okay, all right, that's all you need to do. Okay, all right, sketch. All right, we're not looking for absolute accuracy here, but sketch. The length of the vector, in this case, they are quite different because they are scaled according to their magnitudes. Shorter means what? A lower velocity vector magnitude or lower acceleration magnitude. Okay, yeah, that's about it. It's not too difficult. All right, so long you sit down there and focus a little bit, it's not too difficult. All right, okay. Before I go into conservation of mass, I think the time is just perfect. All right, we're close to 11:30. Okay, let's go for like a 10-15 minutes break, and then we'll come back later. As I said, all right, this is our first lecture. I'm not going to be like a Speedy Gonzalez, you know, and just push everything out, you know. Okay, there's no hurry. Okay, I'd rather you guys understand things than to rush through things. Okay, let's come back 10-15 minutes, and we'll pick up where we last left off. Okay. I shall stop the recording now. Yeah. And I'll re-record the second segment when we come back. Okay, don't worry. Okay, go and stretch your legs.